So here we are reviewing the calculations of the Hess Law and Calorimetry Lab. And before we get started, a couple of basics. We usually know that the Q of the chemicals that we are reacting is going to equal the negative Q of the calorimeter. That's the things we've been talking about. Now, what we're going to do in this reaction is split up the calorimeter and the resulting solution. Since we're doing solutions to each other, the solutions mix into the water and the heat kind of goes into the solution. So it's hard to have the Q of the calorimeter with the solution first when you calibrate. So what we're going to say is the Q of the reaction that happens in the calorimeter, which has the water and of course the solution, is going to equal the negative Q of the resulting solution plus the Q of the calorimeter. Normally, we just do the Q of the calorimeter, or we find the C of the cal, but the Q of the calorimeter, and we're good, or at least when we calibrate it. But in this case, we're going to separate the solution and the calorimeter only because, again, we cannot calibrate the calorimeter with a resulting solution if we haven't added them together. So what we're going to have is we have this calorimeter. It's basically a styrofoam cup, and we're in constant pressure. So this Q, the chemical on the constant pressure, we're going to have a resulting solution, and the chemicals, when they react, they're going to basically flow heat into the calorimeter, the cup, and the solution. So those are two factors. All right, but don't forget that we're putting this minus sign here, equal and opposite, energy flowing within the system, assuming it's isolated, okay? And that's, again, a big assumption. If it's not terrifically closed, we'll have a lid on it, okay? And it's going to be that styrofoam nested cups that we talked about, but that's that negative sign. So we've been through all this already. So a little difference here is that we're going to have the Q of the solution. So the same thing that we've been doing, though, is somehow we need the C of cal, the molar heat capacity of the calorimeter. That's what we need. And in order to find the Q of cal, we basically take the Q of cal equals the C of cal, that's the molar heat capacity of the calorimeter, times the temperature change. And to solve for the C of cal, which is going to be what we do to calibrate the calorimeter, we're going to say the C of cal is the heat that we add and the constant pressure over the change in temperature. So we're still going to do this part of it, okay? It's just that when we find this C of cal and then we plug it back into this, we're going to solve for the Q of cal, and then we're going to have to do the same thing for the solution, and I'll show you that. But so we're often calibrating our C of cal, okay, to get these values. All right, so we're not going to add an electric heater like we did with others. So we're going to do it a little differently. So what we're going to start with, the bottom line here is we're going to have our styrofoam cup. And in that styrofoam cup, we're going to add 50 milliliters of room temperature water. Okay, 50 milliliters, and that's our room temperature water. That's important. Okay, we're not going to use the faucets. We're going to use room temperature water. Now, we're going to heat some water. Okay, maybe we're going to heat, I don't know, 80 milliliters of water to about 60 degrees or 70 degrees or so. It doesn't really matter, but we're going to get it warm. Okay, and then this is really important. We're going to measure out 50 milliliters of that water. And just before we pour it, we're going to take the temperature. And we do that pretty quickly because temperature is going to change. It's cooling as heat is flowing from the warm solution to the colder environment. So this is what we're going to do. We're going to add this heat. And this heat, or this hot water, is going to act as our calibrating heat to find C of cal. Okay, very important we get that. So we're going to add this hot 50 milliliters of water. So we're going to measure out 50 milliliters of water from a hot beaker that we're heating on a hot plate. And we're going to take its temperature, and then we're going to immediately pour it into the cold water. Okay, we're going to hit collect on our computers. Our computers are going to be measuring the temperature change. And this represents some of the data that we might be able to get. Now, it's important you realize that the thermometer okay, is going to have a tough time knowing the initial temperature as the heat is exchanging pretty quickly. Even the thermometer has limitations how fast it can read. The energy change between the chemicals, the reactions that's going to occur, or at least in this case, the physical change, because it's just thermal heat, is going to be instantaneous. So heat's going to go into the water, it's going to go into the container, and it's going to be fast, but the thermometer can't pick that up. So you might see something like this craziness, and then you'll see a cooling off period as we'll use Logopro. What you're going to do is, in Logopro, you're going to take this graph, this initial part of the graph, and we can't really know exactly what the temperature is instantaneously until we take the best fit line and we're going to extrapolate it all the way to the y-axis. So we'll take the best fit line in a nice region that's cooling, and then we'll do regression line back to this initial point here. And that, when we find the y-intercept, and the y-intercept is our value that the temperature becomes instantaneous. And we can do that with strong conviction. And that temperature that we read off the graph after we do the regression line is going to be our T mix. In this example, my T mixture is going to be 37.41, or we'll do 37.4. Okay, so that's what my thermometer from the computer is reading. T mix represents the temperature, and it really is the final temperature of this kind of system, okay? And it's that instantaneous, the temperature change. Remember, the thermometer can't read the beginning. There's too much changes. The thermometer can't get in equilibrium with the hot water very quickly. All right, so we're gonna now find T average. Okay, so let's review a little bit before we get started with this T average nonsense here. What is this T average? Well, before we did that, remember we poured hot water, 50 milliliters of a certain temperature, into the cold water. And then we measured the final temperature, so to speak, by using the computer. Now the T average is going to be the average between these temperatures of the 50 milliliters of the cold water or room temperature water and the 50 milliliters of the hot water that you poured into the calorimeter. So if there was no heat loss, we would have 57.3 degrees Celsius going down in temperature, and we'd have 21 degrees Celsius cold water going up. They'd meet somewhere. Where would they meet exactly if there's no loss of heat to the calorimeter? Okay, well, all we're going to do is take those two numbers and subtract. So I'm going to take 57.3 and subtract that by 21.0. Now when I do that, when I take the difference of 57.3 and subtract it from 21, or take 21 degrees and subtract it from 57.3, I guess that's the better way to do that. All right. What do I get? Okay, well, I get 36.3. All right, that means it's 36.3 degrees. All right, now I subtract that. That means this distance here is totally 36.3. But again, I want to know what temperature I would be if there's no heat loss. So I'm going to divide that by 2. And what I get by taking this and dividing by 2 is I get 18, let's make it 18.2. Okay, it's rounding that off. So what that means is 21 degrees Celsius, the colder water is going to go up to 18.2. And you may say, well, why 18.2? Why the middle number? I found this total distance divided by 2, and the middle number, it would go up. Remember, there's 50 milliliters of the cold, 50 milliliters of the warm. So it should go directly in the middle. Okay, so let's go find that temperature. 21.0 plus 18.2. Okay, so I'm going to plus 21, and what you get is 39.2. So I should get 39.2. And if you don't believe me, you can take the 57.3 and subtract 18.2, and you'll get 39.2. So the middle number, okay, and I'll make that in red, is 39.2. That would be T average, 39.2. And again, wait a minute, what did we get? We got a T mix that's 37.4. Why is it not 39.2? Why is it lower? If it's lower in temperature, remember temperature doesn't measure energy directly, but there's a link. So this number is lower because some energy was absorbed by the calorimeter. That's important. Okay, so let's clean up all of this so that we can do some more work here. Figure out what our Q of cal is. Now, Q of cal is equal to C of calorimeter, the molar heat capacity, okay, times the temperature change. All right, well, in order for us to solve for the C of cal, the molar heat capacity of the calorimeter, okay, we need a temperature change and we need the heat. That's what we're solving for. So that's our first point. So we need the Q of calorimeter. So to do that, we're going to use the water. We're going to say the Q of the water is equal to, so the Q of the calorimeter, or Q of the water, is equal to the negative Q of the calorimeter. Can't do the calorimeter directly, so we're going to do the water. And what do we know? Well, Q of the water, okay, well, the water is going to be MC change in T, okay? In fact, let's do that up here. Let's make some space up here and do the math. Okay, this graph really isn't all that important. We're not going to take a graph. We're going to go right from the logapro, okay? So we're cool. So we're going to take that. So we know that Q equals Q of the water equals MC change in T. And we know the mass of the water, okay, is 100 grams. We know the specific heat in water, 4.18 joules per gram per degree Celsius. Now the temperature change, this is a little bit different, okay? What's the temperature change that gives us an idea that energy was absorbed or released by the container? Well, right here, party people. So what we're going to do is take the temperature final, which in this case from the data is 37, okay? So we're going to take the T mix, which is this case 37.4, and we're going to subtract, so this is T mixture. It's like our final temperature, right? After the, I know it's like the initial in the curve, but it's the final after the heat was transferred, minus, in this case, T average. Why T average? Because this is going to give us the hint of what the temperature is supposed to be. For instance, if we didn't have any absorption of heat, the T mix and T average would be the same. Okay, some of this 39.2 became 37.4 because some heat went into the calorimeter. So we're going to subtract the T average from the T mix to get that difference. So that's 39.2. And you can think of that is the initial temperature if you want. You know, if you think about temperature initial, and this is temperature final of the experiment. This T mix is always temperature final of the experiment. So we plug in our handy dandy calculators and we can do this 100 times 4.18 times the parentheses of 37.4 minus 39.2, close the parentheses. And what I get is my Q of the water is equal to negative 752.4 joules because my specific heat had joules in it. And this is Q of, oh, that's a G, I think. So Q of my water is what I want to do there. All right, now let that erase on its own there. So we got Q of the water equals that. Q of the calorimeter is a negative value, right? So Q of the water equals negative Q of the calorimeter. So if you really want to, put a negative on all of this, and negative times negative is a positive. So Q of the calorimeter is 752.4 joules. This represents the energy that was absorbed. Notice the positive value. We're not getting rid of negatives. Okay, the Q of the calorimeter absorbs some heat. That's the reason why the final mixture is not 39.2. It would have been if there was no heat absorbed by the calorimeter or the air. Okay, so what do I do from here? Well, from this point, I have Q of the cal. Now I have this value, okay, and now I want to get this value. So let's get rid of this stuff, and let's go find what we're going to do next. So, my friends in chemistry, here we go. We're going to solve for my C of cal. Okay, so this would go 753 joules. I'm going to round. All right, and now we have Q of cal equals C of calorimeter times the temperature change. So when we solve for C of calorimeter is equal to the Q of cal over the temperature change. Well, what do we have? We have the Q of the cal of 752 and the temperature change. Now, we're not going to use this temperature change again. That's silly. That was to figure out how much energy was absorbed. Now we want to see, okay, how much in the temperature change of the entire system. So this was the heat absorbed by the calorimeter, right? That's the heat absorbed by the calorimeter. In what kind of temperature change of the system? So what we're going to do is we're going to do our T mix, which is 37.4 degrees Celsius. That's my final minus, okay, my initial. Okay, in fact, now, so again, this is my T mix, it's my final, and my initial temperature before it got warm was 21.0 degrees Celsius. So if you notice here, to get my C of cal, okay, my molar heat capacity, this is what we're doing. Don't forget, this whole process is we're calibrating our calorimeter. We're doing T mix, which is our final temperature always, minus the initial temperature. In this case, the initial temperature is of the cold water. So we're going to do that. Okay, 752 divided by parentheses of 37.4 minus 21, close the parentheses, and what I get rounding off the 3 sig figs is 45.9. All right, so that would be 45.9 degrees Celsius. Okay, that would go in there. Of course, and it's joules. Sorry, my voice. Joules per degree Celsius. So that'd be joules per degree Celsius. 49.9. Okay, and that's the hardest part. So once you have C of cal, we're off and running. So let's continue in this process. So let's continue with part 2 and the rest of the part where we're going to do chemical reactions, and you're going to do 3 of them. And with those 3 reactions, you're going to calculate the Q of the reaction, which is equal to the delta H of the reaction, because of course this is Q at standard pressure. And with these delta H's in these 3 reactions, we're going to do Hess's law and see if we can prove that there's some interconnectivity with the delta H's. But before we do that, you're going to have to figure out the delta H or the Q of the reaction, or the delta H of the reaction. So this is a little different than the part 1 where you did calibration of the calorimeter. We're going to use the value of the C cal to help us. And let's not forget here, we have Q of the reaction is going to equal negative, don't forget the negative, okay, of the Q of the solution plus the Q of the calorimeter. Okay, that's important. And the reason why we're separating this again is because we don't have the solution to calibrate in the beginning once we pour that in, so we had to do it that way. All right, so what do we have here is T mix. Now T mix represents the point where we added the two solutions of the two chemicals. This time it's not water, and they're both at this room temperature number, and we pour one into the other into the calorimeter, which is our styrofoam cup, and we take the temperature. And using the computer temperature probe is going to have a tough time calibrating itself or getting into an equilibrium to measure temperature in the beginning part. What you're going to do is find the most straight line at the end, and you're going to do a regression line, and you're going to find that point right there, which is the y-intercept. The computer will help you find that y-intercept, and that y-intercept is the T mix. Okay, in this case it's 35.9. So how do we do this? Well, let's get rid of this graph here. We really don't need this graph. We're going to do it on the computer. Okay, so let's do that. Very simple. Okay, Q of the solution is equal to the mass, specific heat, change in temperature of the solution. Well, now the mass of the solution is not going to be 100 grams. Yes, it's going to be 100 milliliters, but the density will not be 1. In fact, the density for all your solutions is going to equal gram per milliliter. So the density for your solutions in the 3 reactions you're going to do is going to be 1.1. Oh, I'm sorry, 1.2 grams per milliliter. So if you take your 100 milliliters, which is your result for all of the 3 reactions, you'll have 50 milliliters of each. Okay, for the 3 reactions, and times it by for every 1 milliliter, there's 1 gram, and I'm sorry, there's 1.2 grams. We're going to get 102 grams. Okay, so that's what goes here. Specific heat will be 4.18 joules per gram per degree Celsius. And a change in temperature, okay, it's going to be what? Temperature final minus temperature initial. Temperature final is always going to be T mix. So a T mix that we get from the graph is 35.9. And the initial temperature is the initial temperature of the cold water, 22.9. So let's go find that temperature change using our handy dandy calculator. 35.9 minus 22.9. And I get on the button 13, so I'll put that in there. So that gives me the 13 degrees Celsius. Everything should cancel except for joules. So let's go find 13 times 4.18 specific heat of the water, which by the way is about the same as the solution since it is a dilute solution, times 102. So I get total Q is 554, and I'll make this 3. Actually, to make this 3 sig figs, and joules, and that's what this is right here. 5540, and the Q of cal. That's an easy one. Okay, Q of cal, we already have the value, right? So the Q of cal is the C of cal times the temperature change. Well, the C of cal is 45.9 joules per degree Celsius, and the temperature change is still the same, 13. Multiply them together, 13 times 45.9, and you get 597. Let's round that off to 3 sig figs. 597 joules. Put that in there. 597 joules. Add these two guys together. 597 plus 5540, and you get 6137. Now hold on. these were all positive values, I got to throw a negative in front to make this. So Q of the reaction is going to equal a negative. Okay. Now the Q of the reaction is a negative 6.1, let's make it 40 joules. But what is this kilojoule per mole business? Well, if you look at the reaction, there's a coefficient of 1 for all of them. So no matter what I divide by, I can divide by per hydrochloric acid, per this guy, per sodium chloride or water. Since they're all coefficients of 1, okay, you think I divide by 1, but don't forget, okay, we were using 2 molar solutions of these guys. Yes, they're all stoichiometrically the same. They're all 2 molar. Now, 2 molar solution, and we had what? 0.05 liters, right? We use 50 milliliters. So let's go find the moles. So 0.05 times 2 molar. And what I get is 0.1 moles. So every one of these reactants that we used was 0.1 was 2 molar, and that's given to you in this problem. That'll be the same for the homework. So all of these that we're given is 2 molar, which means what? Which means that we're using not 1 but 0.1 for every one of these. So when we find kilojoules per mole, we've got to take this 6140 number and divide by 0.1 mole. Okay, so when we do that, probably don't need a calculator hopefully for that, but if you need to, you see that it gets bigger by 10. Okay, and that's 61400, and that's of course joules, and of course we convert to kilojoules. It becomes what? It becomes 61.4 kilojoules per mole. And that's what this number is. And then we can make it 61.4 kilojoules. And you would do that for the 2 other reactions just like that. Take the same out, pour them together. Okay, using room temperature, use the computer and the Logopro and the heating probe to find the T mix, and go through the same calculation for the other 2 reactions. I'm not going to do that. And then you do your Hess's Law. Once you have your 3 delta H's, you're going to use 2 of them and manipulate them to get the third. And you're going to see if in fact the energy that we get from calorimetry and using Hess's Law can be validated. And I'll talk more about that, but this is the calculation part. All right. Now I want you to go and do the other reaction based on the other worksheet I gave you and enter that in the form. Okay, good luck.